Swayam Prabha. Digital India. Educated India.
Good morning, students. Let us take up another example in the three-dimensional structure. So this is regarding a plank here, ABCD plank, so which is supported on the wall here along AB, which is at an angle of 30 degrees from the horizontal. So, and then it is supported at these 2 points A and B by hinges. So hinges about which, it's almost like point hinges about which the plank or this board can rotate about the AB axis. So essentially the ABCD board can rotate about the line AB and being supported at these 2 points A and B, right? And then it has its weight obviously at G, acting vertically with a value of W is equal to mg, and then it is supported at point D, and it is connected by rope to a point E here as shown in the figure. So this is the horizontal surface you can imagine. And so this B and E are on a horizontal line and AE is vertical from this axis. So here this M is (40 kgs) and okay, so we are supposed to find out what is the force or what is the called tension in this rope DE, and also what are the supports at A and B, support reactions at A and B. Okay, so this is a three-dimensional structure and a single body, of course. So a single body, when it is acted upon by forces, so if it is under equilibrium, we have 6 scalar equations. That means that sigma F is 0. Okay, all the forces should add up to 0, and similarly the moments, sigma of all the moments of all the forces about some point is 0. So since both F and M are vectors, so each of them is equivalent to 3 scalar equations. So let's try to draw the free body diagram. In the free body diagram, if you draw the same thing but in dotted line, the supporting structure. This is the wall. Okay, so this is the plank, and at A and B and D, so here it is being acted upon by forces. Let's represent the forces here. One is W here, and then at point A it is acted upon. Well, let's just see this one. So this is the tension of the rope, and this is 30, this is 2400, this is 1200, and so on. So if this is 2400, then this height here is, this height AE is nothing but 2400 into sine 30, 1200, right? So then we have forces at A, and then we have forces at B. So usually what happens is that since this is slightly inclined downwards here, so at some, either at point A or B, all the forces need to be, all the forces in the sense that all the component of forces in XYZ direction should be acting at A, right? And then at B also is that, so since it is sliding, so we have to have forces in this, support in this direction, whereas at B we don't need to support it to slide it along the axis, but however we need to support it in the other two directions. So let us choose the axis in such a manner so that it is convenient for us. Okay, so let us choose the axis like this one, X, and this is, we choose this to be Z axis, and then perpendicular to this we have Y axis. Okay, so the X is along this smaller side and Z is along this axis AB, and then we have Y the perpendicular to X and Z. Okay, and of course it's the right-handed system. And so why we have chosen this axis is that, so similarly here of course the same axis, and here we show the three forces because this is a point support. So we show these three forces here at point A. So this we call as AZ. So AZ is the force, and this is AX, and here this is AY. Yeah. So this also I have to remind you that many of these examples I have taken from the textbook by Merriam and Craig. So this has been taken from edition 5. I think the number also has been shown there, 3.92. So the problem has been taken from there, and then I'm supplying the solution. So just to keep his nomenclature, so the forces are represented as, instead of saying that FAX and FAZ, so it's convenient sometimes just to represent AX, AY and AZ as the force component acting in X, Y and Z direction. Okay, and so similarly here we need a BX and BY. BX, and the one thing which you have to understand here is that we don't require a BZ force. Okay, we don't require a BZ force component because there is one AZ here to support it in the Z direction, and we don't need any other force here. Okay, and furthermore, why we have taken that is also is because that if you look at the number of unknowns here, weight is given to us, weight is equal to mg, and tension is the unknown which we need to find out. And then we have ax, ay, and jz, 3 here, and bx and by here. So 2. So totally you have 6 unknowns. Okay. So using these 6 unknowns, so we will be able to find out all the components. So if you introduce unnecessarily a bz there, so we will not be able to solve it because it is a 7th unknown, and either we have to put a constraint in that z direction, okay, or we have to let it be free without any loss of generality. Let it be free in the sense that this point here will have a little freeway. It's free to move in the direction of z. Okay, so like that. So there are 6 unknowns. Anything more than that, if you introduce that bz, so we'll have to put a constraint. So constraint in the sense that it is saying that it is half of az, or it is completely constrained, or az is 0, only bz is there, and those kind of things. So without going into all those kind of unnecessary constraints, so we just show ax, ay, az, and bx and by. And the 6 unknowns are t and components ax, az, and bx and by. Okay, so these are the 6 components, and then we will have 6 equations, right? To start with, so all these things are vectors, and of course we have x, y, z axis like this, so we can use here a is nothing but the total force. A, you can write it as axi I'll use the white. axi okay, and we are assuming that B has only Bxi and okay. So another important thing is that this XYZ is also very convenient, those directions along the, particularly along this axis Z. We would like to have one axis along this line AB about which the door can swivel. Okay, so why we require it? So that means that when the door can swivel about this AB, means that when it is going to, when you're going to solve these equations, so the moment about AB, so that means that the Z axis need to be 0. Okay, so that the door is completely under equilibrium about this Z axis, about this AB line, so that the door is completely, will not have any tendency to rotate. Okay, it has a tendency to rotate, but its moment about the Z axis is 0, so then it's under equilibrium. So that is why the AB has been taken. Okay, I hope you have understood that. So why we are taking the Z axis along AB is that while calculating, we let the mz to be 0 at on this line. So starting from A, if you draw a Z axis, so that means that mz is 0. So this is about B, and then we have W here. So W, and so this is 30, and so this angle is 90. So this is 30 here that's not exactly 30. So what we try to draw is we will draw a perpendicular here to this line. So I hope that this is a 90 degrees. AE makes with the horizontal a 90 degrees, and then from E we are dropped perpendicular to this line. So this is a z-axis, and if you drop a perpendicular to z-axis, so since this y-axis is in the same plane as this vertical wall, so we'll drop 90 degrees and this will be parallel to y-axis itself. So it is a 90 degrees here. Looking at, so this dropping this perpendicular, the drop here comes on to the point H. Okay. So like this, so we have, so what is that which how we are going to implement the equilibrium equations? Okay. One thing is that the total forces in x direction, in y direction, in z direction are to be 0. So, and so similarly, the moments. So why we take the moments is that, if we want to take the moment about A of all the forces, then you can see immediately the advantage that all the forces Ax, Ay and Az about point A here is 0, and many of these things Bx, By, its moments also about A can be 0. So leaving only the moment of T about A as well as the weight about A. Okay. So what we follow here, just like in the earlier problem, what we use is that, so if you want to find out moments about A, so of say for example T, so the moment of, we will apply the moment equilibrium equation. Of say MA. So sigma MA is 0 of all the forces. So let's try to find out what are all the forces here. So one thing is T, and the moment of any force, as we have seen in the last problem, is that if you have any so we have seen in the last class, so then if it is at A, this is, let me just, this is about A, this is the position vector of A. So the moment of about O is simply, you know that is R cross A times F. Force F is acting at A, and then RA is the position vector up to A, and if you take a cross product, so that will give you the moment about A. On the other hand, it's also possible that if you have point B here, so if you want to calculate about B, then it is nothing but the BA vector cross AF. So this sometimes is also written as position vector of A with respect to B times the vector f. So sometimes we will write it like this one. So position vector of with respect to B, that's what we call as BA, is nothing but RAB times cross F. Okay, so this way we will get the moment expressed as a vector straight away, and you can resolve it into x, y, z components. So similarly here, coming back to this one, so we need to apply the, so this is acting, T is acting, if you write T as a vector, so it is nothing but the magnitude of T and along DE. So what is this representation? So this is nothing but the vector DE. So this cap means that it's a unit vector. So its magnitude is T and in the direction of DE. So DE cap is nothing but, as we had done in our last problem, along DE. That's number one, and then we can also write it like this. We can also write it. So that means that if you can have a vector DE by itself and divide by its magnitude, then that will give you a unit vector along DE. So this is how we represent a force. So this T is acting at D, and then if you want to take its moment about, so moment of T of T, say we will take about point A, so it's nothing but, so since acting at D, so we can say that it's position vector of D. So for D, you can say that, so it's nothing but simply cross. Okay, so this is the position vector of D. So that's right from, this is the origin. So AD is the position vector of D by itself, and then the vector T along this one. So this is what it is. And let's try to do this one. RD is easy to find out. RD is nothing but what? This distance is 1200 I. So it is in the direction of X, so it's 1200 I. And T is the one which we need to find out. For that we require DE. Okay, so for that what we require here is that the DE, so that means that DE vector is nothing but RE minus RD. So RE is what? So it is in the X direction. So it is X direction is, so it is in the plane of YZ. So there is no X component, and E point is in the vertical plane, right? It is in the YZ plane. So there is no X component. And what about the Y component? Y component is nothing but DE, right? So DE is nothing but 200 root 3 by 2, because this is angle 30, right? So horizontal to this one, horizontal to this is 30, and vertical to this one is again a 30. So this is J. And then in the Z direction it is AH. So how much is H? It is this is 1200, and opposite to that sine 30, so it is 600 K. Okay, and here this is RD is minus. So DE, if you put it, it is minus 1200 I plus 600 root 3J and 600K, right? So this is the magnitude. So if you want the unit vector, it is nothing but dE by, you can find out the magnitude of dE, and if you divide by that, so what we get here is minus 0.707 I plus 0.612 J 5536 K. Okay, so this is the unit vector along DE, and so the vector, finally the vector that's a force in the rope can be written as T times, this is the magnitude and this is the direction, right? So this is the T, and so finally what we have is that we have RD and we also have T expressed as a vector. So if you substitute this into this one, so then we will get the moment of this T about this one. So then the other forces are the W itself. The weight here, moment of weight W about A, that is the origin point. Okay, so this is nothing but R of G cross W as a vector here. So the vector here W is actually vertical, but then with reference to this XYZ axis, so we have, so it is slightly like this one and this one. This is y-axis and say, let's say prime. So this is with respect to, because this is, y is not really vertical, it is bent by 30 degrees from the vertical. So this is actually the vertical in the absolute sense, but the actual y is 30 degrees from here. Okay, so similarly, so W will be making 30 degrees with respect to the y-axis here. So if you look this one, so it is actually mg and it is in the direction of y is up there. So it is actually minus j mg times cos 30 j, right? And then this is not x-axis, I'm sorry, this is z-axis. And it is in the z direction, again in the opposite direction of that, and it is mg sin 30 k, right? So W is vertically downwards in the actual sense, but however this y and z are slightly inclined by 30 degrees, and so it is cos 30 here and sin 30 there. And so similarly here, the position vector of the center of gravity here, Rg, is how much? It is in the direction of x, it is 600 I, and there's no y. There's in the z direction it is 1200. Okay, so moment of weight is now, it is Rg is 600I plus 1200J cross here. I can take out mg out, minus cos 30 j and minus sin 30 k. Okay, so this is here. If you want, I can also write here for the moment of t. Moment of t is Rd, that's 1200I cross this one. If you want t, you can take it inside. So this is fully what is mt, and this is what is mw. And what else is there? Then there's also a moment due to B, force B at point B. So the force is, B has two components, Bx and By. So it is Bx I plus Byj, right? And this is about B. And where is it acting? So it is acting at point B, so which we can write is only in the k direction, 2400 k. Okay, so now we can say that moment of the force B, not about B, please consider here subscripts I'm using for the forces. This is m of t, this is m of w, this is m of B here. So it is nothing but RB cross okay. So RB is 2400 K, and B here is that. So this is completely using the vectors. So in fact, if you can see it, interestingly, is that okay, we'll come to that. So this is using the vectors here. So now making moment about A of all the forces is that this one mt, which is 1200 I cross minus 0.707 t I plus 612 tj and 0.553 t. So there is a t everywhere. So component of t appears in the I and j and k. And then the weight of moment of the weight here. So it is 600 I 1200 J times mg minus cos 30 okay, this is of this, and of b, so we have last one, so 2400k bxi and by j. So the whole thing will be 0. The sum of all these things put together will be 0. Okay. So you can simplify it, and if you simplify it, the first one, for example, simplifying, if you simplify this one, so what we get here, this is I cross I, so that is 0, and this is I cross j, which is k, so it is 1200 times 0.612 t k, and this is I cross k is minus j, so it is minus 1200 553 t j, right? And so similarly here we have two things here, I cross j and I cross k for the first one, so 600 mg, I cross j is k, so it is minus cos 30 k, and I cross k is minus j, and minus minus plus, and it is sin 30. This is about I, and the same thing is there for 1200. So j cross j is 0 and j cross k is minus, so it is sin 30 I, right? And so similarly here, the last one is 2400, k cross I is j, and k cross j is minus I. So this is how we get this equation. Okay, so you can collect the terms. What is the term which we would like to? There's a equation. If you collect the terms for I, you get one expression, and j for one other expression, and k another expression. And if this equilibrium equation has to be satisfied, then each of these components need to be 0. So that means that if you collect it, you will have I and k, and each one of them has to be 0, right? If your interest is now to try to find out t, okay, if your interest is to find out t, then which component which we would like to take. Okay, so if you look at this one, bx and by are the unknowns together with t, right? And of course mj is given to us. So the bx and by are appearing as I and j, and so that means that if you can get an equation in k, then what all you require here is that 1200 into 0.612 here t, right? This is k, and here you have another k, so it is minus 600 mg cos 30. So this is k here, and then there is no other k here, that's all. So this is the interesting part which you have to always keep in mind. So if you are interested only in finding out t here or here, so you should see the other unknowns are appearing as j and I. So avoid that equation I and j, so they will be appearing here and here. T also might be appearing here, but however T appears only in the K component. So if you solve for this one, M is 40 kgs, and then if you solve for T is newtons. Okay, so this is, so after calculating T, you can make the equation for I, you can make the equation for J. Okay, so make the equation for I and J, then you can solve for, so you can solve for Bx, By using Mx and My equation. Okay, you can do that. So that means that you can solve for Bx and By using this moment equation. What about these things, Ax, Ay, Az? So these are easy to find out by invoking the equilibrium equations in the force. So that means that for Ax, for example, in the x direction, you have Ax here and a Bx here, Ax plus Bx, and together with anything here, the T also has a component here, and so you have to look for Tx, and together they make one equation. So like that, you have an equation in Y, you have an equation in Z. So you should be able to solve for Ax, Ay, Az. So I think I'll leave it as a homework. Okay. So we have done everything very systematically using all vectors. But on the other hand, if you are interested in finding out only T, so this you could have realized right in the beginning. So this part, if you realize right in the beginning that if you take the component of all the forces about this axis here, okay, at point A about this axis, then you can very well see that about this axis, all these three components will not have any moment. These will not have any moment about this axis. So only the forces that have component is the T and W. That's all. So you will have components here. So you find out what is the T here. T in the vertical direction. T in the vertical direction here will have a moment about this, and W in the vertical direction. So this WY will have a moment about this axis. This ZW, the Z component will not have any moment about this. So that is exactly what this equation is all about. So this equation is just the Y component of W, and this is the moment arm here, 1200, and so you will have the moment about AB, and this is nothing but the moment of weight about the axis AB. So you could also have done it that way. That is another smart way. Or if you are really a little scared about the three-dimensional nature, so you can go through the vectorial approach. So I think I'll stop here, and in the next class we are going to start the principle of virtual work. Okay, so that is another very powerful principle, just like Newton's laws, but it is from another angle of work and energy. Okay, so for the moment it's bye.